Okay, good afternoon everyone. I hope you're all good and I hope you stay safe and healthy. Okay, remember our last topic was the finding solutions for systems of linear equations, right? The first method was using the algebraic techniques and we used the substitution and the elimination methods to find solutions for systems of linear equations. The second one was the graphical method. The third one was the method using determinants, which we called Cramer's method. And here we go with the fourth method, which depends on matrices, and it's called the inverse matrix method. We reviewed some important forms of matrices last lecture, if you remember. We said that the matrix is merely an arrangement of objects, but these these objects or numbers are placed between brackets and not like the determinants between parallel lines. We also said that the dimension or the order of the matrix doesn't have to be like the determinants in which we have the number of rows have to be equal to the number of columns. Here the number of rows and the number of columns can be different. That's why we gave the matrix the notation m by n. And we took some examples of matrices, and we mentioned that matrices don't have values. This is not like a determinant which is a value that we need to evaluate. No, matrices are just arrangements of numbers between the square brackets. Example for a 2 by 3 matrix, because it has 2 rows and 3 columns. This one is an example of a 3 by 2 matrix because it has 3 rows and 2 columns. And this one is an example of a 3 by 1 matrix because it has 3 rows and only 1 column. And this one is an example of a 2 by 2 matrix as it has 2 rows and 2 columns. We also reviewed some the general form for the matrices, which is a matrix of order m by n. In other words, we have m different rows and n different columns, so we call the order m by n. We considered some special matrices. The first one is the row vector, which consists of is a matrix which consists of only one row and any number of columns. So we give it the notation the matrix of order 1 by n. And we also has the column vector, which is a matrix that consists of any number of rows but only one column. So we call this an m by 1 matrix. We also have the square matrix, and this is a matrix in which the number of rows is equal to the number of columns. So we have here an example of a 2 by 2 matrix having only 2 rows and 2 columns. This is an example of a 3 by 3 matrix that has 3 rows and 3 columns, and so on. So a square matrix is a matrix in which the number of rows and columns are equal. We also consider the diagonal matrices, which is mainly a square matrix. First, it's a square matrix where all the elements are equal to 0 except the elements on the main diagonal, and we call the main diagonal the elements with the subscript A11, A22, A33 up till ANN. So the diagonal matrix has to start with has to be a square matrix, and then we have another condition that all the elements are equal to 0 except those on the main diagonal. They can be any value, but all the other elements have to be equal to 0. We then have the identity matrix. The identity matrix is a diagonal matrix, but with the condition that all the main diagonal elements are specifically equal to 1. This is denoted by I, and it plays the role of 1 in numbers. Remember, in numbers, if you multiplied 1 by 3, you will get 3. If you multiplied 1 by 10, you will get 10, and so on. The same holds for identity matrices. If you multiplied the identity matrix by any other matrix, you will get this other matrix. For example, here I2 is an identity matrix of order 2 by 2, so we give it the notation I2. And this is the identity matrix, so we give it the notation I. All the off-diagonal elements are equal to 0, and all the main diagonal elements are equal to 1. Then we have I3. This is an identity matrix of order 3, in which all the off-diagonal elements are equal to 0, and all the main diagonal elements, as we can see, are equal to 1. And the same holds for IN, in which we have all the off-diagonal elements equal to 0, and all the main diagonal elements are equal to 1, but the order of the matrix is n by n. Our next matrix is the null matrix. This is a matrix with all elements equal to 0, so we give it the notation phi, and it can be of any order. There is no restriction on its order. It doesn't have to be a square matrix, it can be of any order, and it plays the role of 0 with numbers. If you added 0 to any number, you will get the same number. 0 plus 2 equals 2, 0 plus 5 equals 5. The same thing holds with the null matrix. If you added the null matrix phi to any other matrix, you'll get this other matrix. Then we have the transpose of a matrix. We already took the transpose with determinants. When you needed to get the transpose of a determinant, we just flipped the rows into columns and the columns into rows. This is the same thing that we need to do if we are to get the transpose of a matrix. We just turn the rows into columns and the columns into rows. If the original matrix is called A, then its transpose is denoted by A prime. Let's take an example. If this is a 2 by 3 matrix consisting of 2 rows and 3 columns, and we need to get its transpose, which we call A prime or A dash, we'll just go to each row and flip it to be a column. So we'll get a matrix A transpose or A dash of a flipped order. Instead of having A being a 2 by 3 matrix, A prime or A dash will be a 3 by 2 matrix, and each row in the original matrix A will be a column in the transpose A prime, as you can see. Another matrix is what we call the symmetric matrix. A symmetric matrix has the condition first that it has to be a square matrix, and then it's not only a square matrix, it's a square matrix for which the matrix is equal to its transpose. So if we have a matrix A, which is a square matrix, and we got the transpose, and the transpose A dash or A prime is equal to A, we call this a symmetric matrix. Let's take an example. If this is a matrix A, this is a square matrix. If we got the transpose A prime or A dash, we will just flip each row to be a column and each column to be a row. So we'll get A prime as 2, 5, 5, 3. And as we can see, A is exactly equal to A transpose. That's why we call this matrix A a symmetric matrix. Another example, if you have another square matrix of order 3 by 3, and we call this matrix A, and we need to get its transpose, we will just go and flip each row to be a column and each column to be a row to get A prime or A transpose. But as we can see, A is exactly the same as A transpose, which means that the matrix A, the square matrix A, is a symmetric matrix. The last special case of matrices is the singular matrix. A singular matrix has to first be a square matrix, so this is the first condition, it's a square matrix, and the second condition is the value of its determinant is equal to 0. So if we have a square matrix and we got its determinant and we found that this determinant is equal to 0, we call this matrix a singular matrix. For example, the matrix A here is a 2 by 2 matrix, a square matrix. If we got the determinant of A, we just remove the square brackets and write the numbers between parallel lines as we did with the determinants, and then the rule is that we multiply the 2 by 4 and we subtract the 8 times 1, so this will be 8 minus 8, which is equal to 0. In this case, the matrix A is called a singular matrix. And if a matrix, we got the determinant of another matrix and it's not equal to 0, we call this matrix a non-singular matrix. So a singular matrix means that its determinant is equal to 0, and the non-singular matrix means that its determinant is not equal to 0. We'll now move on to the operations on matrices. Like numbers, we can add or subtract matrices, but the condition is these matrices must have the same order. They must have the same number of rows and the same number of columns. Once the condition is satisfied, we just go to each two corresponding elements in the matrices and add them or subtract them, as this example shows us. For instance, we have a 3 by 2 matrix and another 3 by 2 matrix, so the condition is satisfied that they are of the same order. We then just go to each two corresponding elements and we add them up. So here we have 2 and negative 1 in the first row. We will add them up to give us 1. We have 4 and 3 in the first row. We will add them up to give us 7. And we'll do the same thing for each two corresponding elements, the 3 and the 2, the negative 1 and the 4, the 5 and the 1 and the 6 and the 2. And exactly like numbers, you have to care about the order when you subtract matrices, but you don't care about the order when you add them up. So we have this note: if you have two matrices that are of the same order, you can say that A plus B, the matrix A plus the matrix B, is exactly equal to the matrix B plus the matrix A. In other words, the order of addition doesn't matter with matrices. Just like numbers, if you have 2 plus 5, this will be exactly equal to 5 plus 2. But with subtraction, also like numbers, the order of subtraction will matter. So A minus B is not equal to B minus A. And we say not necessarily equals to B minus A, because sometimes in some special cases we might find that A minus B is the same as B minus A, just as a coincidence or something. But in general, the rule is A minus B is not equal to B minus A, or in other words, the order of subtraction matters. Our second operation on matrices is the multiplication of a matrix by a scalar. And by scalar we mean a constant value or a number, any number, positive, negative, zero, fraction, any number. And in this case, we multiply each and every element in the matrix by this constant or the scalar. So for example, here we have a 2 by 2 matrix and we want to multiply it by 2. This is done through taking each element in B and multiplying it by 2. So we have 4, 12, 18 and negative 2. Each element here is multiplied by 2. Remember, this is different from the multiplication by a constant or a scalar with determinants. In the determinants, we only have to choose one row or one column and multiply its elements by this constant or scalar. But with matrices, each and every element is multiplied by the constant 2 as we see in this example. Our third operation on matrices is the multiplication of matrices. Now we're not multiplying a matrix by constant or a scalar. Instead, we are multiplying two matrices together. And this has a very important condition to be satisfied. To be able to multiply two matrices, then the number of columns of the first matrix and the multiplication has to be equal to the number of rows of the second matrix in the multiplication. So as we can see here, if we are to multiply two matrices A and B, then the number of columns of the first matrix B, here it's called N, has to be equal to the number of rows of the second matrix in the multiplication B here. Okay, so the number of columns here has to be equal to the number of rows of the second matrix B. If this is satisfied, then yes, you can get a result, let's call it C, which is another matrix. But what is the order of this matrix? The order of this matrix will be the number of rows of the first matrix times the number of columns of the second matrix. So this is our order of the new matrix. It will take the rows of the first and will take the columns of the second. So again, this is a very important condition for matrix multiplication. In order to multiply two matrices, they should satisfy this condition. First, that the number of columns of the first matrix in the multiplication has to be equal to the number of rows of the second matrix in the multiplication. So we call them here N and N. Once this is satisfied, then the resulting matrix, the product, will be the number of rows of the first matrix multiplied by the number of columns of the second matrix. So this will be M by K. Okay, let's take an example on matrix multiplication. Assume we have these two matrices, the matrix A, which is a 2 by 3 matrix, and the matrix B, which is a 3 by 2 matrix. Okay, let's check first if we can multiply A by B. For this to happen, we need to satisfy the condition that the number of columns of the first matrix A, which is here 3, has to be equal to the number of rows of the second matrix in the multiplication B, which is also 3. So yes, the condition is satisfied. Okay, what about the product AB? The product AB will have the number of rows of the first matrix and multiplied by the number of columns of the second matrix. This is the order of the resulting matrix AB. Okay, but how do we get the values inside it? We start with each row of the first matrix. So here we'll start with the first row of A, and we multiply it by each column of B. So we take the first row here. To find the first element in the product, we take the first row here and multiply each element in the first row by its corresponding element in the first column, which is we multiply the 1 by the 4, and then add it 2, multiplying the 0 by the negative 2, and then add it 2, multiplying the 2 by the 1. This will give me the first element in the resulting product matrix. Once we're done with the first row and the first column, we will go to the first row and multiply it by the second column in exactly the same way. We'll go to the 1 multiplied by 3 plus 0 multiplied by 0 plus 2 multiplied by 2. Now we're done with the first row. The first row is once multiplied by the first column and the second time multiplied by the second column. We now move on to the second row, and we'll go to the second row and multiply each element in the second row by each element in the first column. So we'll go to 3 multiplied by 4, and then add this to 4 multiplied by negative 2, and then add this to 5 multiplied by 1. Once we're done, we'll take the second row and multiply it by the second column in exactly the same way. Okay, let's see this. applying this on the matrices A and B, we can see that we start with the first row here and multiply each element, as we said, by the corresponding element of the first column of B, and then we'll add these up. So here we have 1 multiplied by 4, 0 multiplied by -2, 2 multiplied by 1, and then we add all these up to give us 6, which is the first element in the first row and first column of the product AB. We're done with the first row multiplied by the first column, so we'll move on to multiplying the first row by the second column in much the same way. So we'll multiply the 1 by the 3, and we add this to 0 plus 0, and then we'll multiply add this to 2 multiplied by 2, giving us the 7 here when we add all these values up. Once we're done with multiplying the first row with each column in the matrix B, in the second matrix, we move on to the second row, and we do exactly the same thing we did with the first row. We multiply each element here with each element in the first column of B. So we have 3 multiplied by 4, and here we have 4 multiplied by -2, and then we have 5 multiplied by 1. Adding these values will give me 9 here. Then we'll multiply the second row by the second column. So we have 3 multiplied by 3, 4 multiplied by 0, and 5 multiplied by 2, giving us the 19 we have here. Okay, but we have to take care that the order of multiplying matrices is very important. So the product AB is totally different from the product BA. Okay, the AB, as you can see here, is a 2 by 2 matrix, and these are its elements. Okay, but the BA is, as you can see, this would be we'll take the number of rows of B, so it's a 3, and the number of columns of A by 3 matrix. So if we try to get the B by A, which is the product of a 3 by 2 matrix and a 2 by 3 matrix, the condition is satisfied because the number of columns of the first matrix B is 2, and the number of rows of the second matrix A is 2. So yes, we can multiply B by A, but the resulting matrix will be a 3 by 3 matrix and not a 2 by 2 matrix like the A and B. So to verify that the matrix multiplication AB is not the same as the matrix multiplication BA, let's do the BA. We're done with the AB, and it's a 2 by 2 matrix, and we got its elements. Now let's multiply the B by A, so the order makes a big difference. Now, to satisfy the condition of matrix multiplication, the number of columns of the first matrix has to be equal to the number of rows of the second matrix in the multiplication, and this is satisfied. And the resulting matrix BA will take the number of rows of the matrix B and the number of columns of the matrix A. So we have here a 3 by 3 matrix. How do we get its values? In much the same way that we did with the AB. We go to each row of the first matrix, which is now B, and multiply its elements by the corresponding elements of each column of the second matrix A. Okay, so we'll start with the first row here, 4 and 3, and we'll multiply its elements by the elements of the first column of A. So this means we have 4 multiplied by 1 plus 3 multiplied by 3. And this is our first element in the 3 by 3 resulting matrix. Now we'll move on to multiplying the first row by the second column in much the same way. So we have 4 multiplied by 0 plus 3 multiplied by 4, and this is the second element. Then we multiply the first row by the third column. So we have 4 multiplied by 2 plus 3 multiplied by 5, and this is our third element here. Once we're done with multiplying the first row with each possible column in the second matrix, we move on to the second row and do exactly the same thing. We multiply the second row by the first column of A and write the results here. We multiply the second row by the second column of A and write it here. and we multiply the second row by the third column of A and write the results here. Once we're done with multiplying the second row of B by all the possible columns of A, we move on to the third row and do what we did with the first two. We multiply each element of the third row with the corresponding elements of the first column of A and write the result here. And then we multiply the third row by the second column of A and write the result here. And we multiply the third row by the third column of A and write the result here, giving us the matrix BA, which is a 3 by 3 matrix, and this is totally different from the matrix AB, which is a 2 by 2 matrix. So yes, the order of multiplication of matrices is very important. We'll now move on to our last operation on matrices, which is finding what we call the inverse of a matrix. Remember, with numbers, if you have 3 and you want to get its inverse, we say that the inverse of 3 is 1 over 3. Why? Because multiplying 3 by 1 over 3 will give me 1. Okay, this is for numbers. We will do the same thing for matrices. Let's first define what's the inverse of a matrix. Assume we have two square matrices A and B, and we say that we found the product AB and we found the product of BA, and both of them was equal to the identity matrix of the same order. So when we multiplied A by B, we got the identity matrix, and when we multiplied B by A, we got the identity matrix for these two square matrices. In this case, we say that B is a special matrix which is called the inverse of A, and we give it the notation A as if it's A raised to the power negative 1, like this. And we can say now that if A inverse is the inverse of A, then it satisfies the condition that multiplying A by A inverse from the left or from the right, here the order doesn't matter because they are square matrices and their product is always the identity matrix, then we call this A inverse, we call A to the power negative 1 here the inverse of the square matrix A, satisfying which condition again? That the product of A and A inverse is equal to the identity matrix, and the product of A inverse and A is also equal to the identity matrix. And let me remind you of the identity matrix. It is the matrix, it is a diagonal matrix, which is a square matrix where all the elements are equal to 0 except the elements on the main diagonal are all equal to 1. Okay, so and we said that the identity matrix plays the role of 1 with numbers, so this is why we call A inverse and A the inverses of one another, because when we multiply them, either A inverse or A inverse A will get the identity matrix, which is the equivalent of 1 in numbers. In order to be able to get this inverse, this A inverse, for any square matrix, so pay attention that we won't be able to get inverses unless the matrix to start with is a square matrix. The matrix has to be a square matrix to be able to try to find its inverse. Sometimes we will find an inverse, sometimes we cannot find an inverse for a matrix. What are the conditions that we can get an inverse? We have two conditions. The first one, that the matrix is a square, as we said, and the second one is that the matrix should be a non-singular matrix. And by non-singular matrix we mean that its determinant is not equal to 0. So to find an inverse of a square matrix, its determinant has to be not equal to 0. If the determinant of the matrix A is equal to 0, which we call a singular matrix, we cannot find its inverse. Okay? To find the inverse again, we need to satisfy two conditions. The first one is the matrix has to be a square matrix and a non-singular matrix, or in other words, its determinant is not equal to 0. If the determinant of the matrix is equal to 0, then we call it a singular matrix, and this means that it does not have an inverse. And this will take us to how to find this inverse. Okay, there are steps for finding the inverse of a square matrix. We'll use what we call the cofactor approach. Okay, the first step is we calculate the determinant of the matrix. If the determinant is equal to 0, then we stop and we conclude that the matrix is a singular matrix and we cannot find its inverse. Otherwise, if the determinant is not equal to 0, we can proceed to step 2. Step 2 is to find what we call the cofactor matrix. Do you remember the cofactors that we used to get the determinant, to evaluate the determinant, which is -1 raised to the power I plus j multiplied by the determinant after removing the ith row and the jth column? This is the cofactor matrix, is a matrix that is obtained by replacing each element by its cofactor. Okay, so we will get the cofactors for each element in the matrix. After we get, and we'll see this using an example, it will be very clear. Then after we get the cofactor matrix, we will get its transpose, and the transpose of the cofactor matrix is what we call the adjoint matrix. So we just go to the cofactor matrix and transform each row to be a column and each column to be a row, and this will give us what we call the adjoint matrix. And then to find the inverse of the matrix, we just multiply the adjoint matrix by 1 over the determinant value. The determinant that we got in step 1 will be divided by 1 and then multiplied to the adjoint matrix. And we'll take a step-by-step example to see how we can find an inverse of a square matrix. Okay, let's see how we can do this, how we can get an inverse of a matrix using an example. Suppose we have the matrix B, a square 2 by 2 matrix, and we need to get its inverse. As we said, the first step is to calculate the determinant, and we have to check whether this determinant is equal to 0 or not. As can be seen here, the determinant is equal to -10, which is not equal to 0, thus we can proceed. In case the determinant was equal to 0, this means that this matrix has no inverse and we will stop. Okay, here the determinant is not equal to 0, the determinant is equal to -10, so we'll proceed to step 2. Step 2 is obtaining the cofactor matrix, and we've already seen the definition of the cofactor before. The cofactor is defined as -1 to the power I plus j, where I is the number of the row and j is the number of the column, multiplied by the determinant obtained after deleting the ith row and the jth column. We will do this for each position. Here, for this one, this one, this one, and this one, we'll get the cofactor for the first row, first column, the cofactor for the first row, second column, the cofactor for the second row, first column, the cofactor for the second row, second column. But take care that we don't multiply by these elements when we get the cofactors. We don't multiply like the determinant we used to multiply by the element itself. Here we don't multiply by the element. We don't multiply by 3 or 4 or 1 or -2, as we'll see on the next slide. Okay, so here we should start with getting the cofactor for each element. Okay, we will start with the cofactor for this position. Okay, we don't multiply by the 3, instead we just write -1 raised to the power 1 plus 1, which is the first row and the first column, because this is the position we are considering now, and then we multiply by the determinant after removing the first row and the first column. Because this is a 2 by 2 matrix, when you remove the first row and the first column, you will be only left with one element, which is -2. That's why we multiplied the -1 to the power 1 plus 1, which is to the power 2, by -2. We'll move on to this position. This position, we won't multiply by the 4 here. 4 will not appear in the cofactor matrix. Instead, we will multiply negative 1 to the power 1 for the first row and 2 for the second column, and then multiplied by the determinant after removing the first row and the second column, in which this 4 is located. It's located in the first row and the second column. If you remove the first row and the second column, you'll be only left with the number 1. It's not a determinant anymore, it's only a number. Then we'll go to this position. In this position, negative 1 will be raised to the power 2 for the second row and 1 for the first column. And then we'll remove the first column and the second row. So we'll be left with only the number 4 here. We'll move to this position. We'll multiply negative 1 raised to the power 2 plus 2, which is the second row and the second column, multiplied by the determinant after removing the second row and the second column, which is not a determinant here also, it's only the number 3. We'll do this multiplications, ending up with the negative 2, negative 1, negative 4, and 3. So this is the second step to get the cofactor matrix, or the matrix of cofactors, in which we go to each position in the original matrix, and we don't write the number itself. Instead, we write its cofactor, which is negative 1 to the power I plus j, multiplied by the determinant after removing the ith row and the jth column, which is what we used for obtaining determinants in the last topic. Okay, this is our second step. We'll now move on to the third step. The third step is an easy step. We just get the transpose of this matrix, and we will call it the CF, or the cofactor matrix transpose. Okay, each row here will be a column here, so we'll have negative 2, negative 1, negative 4, and 3. In the third step, we obtained the transpose of the cofactor matrix, which we call the adjoint matrix, and now we will use it to calculate or to obtain the inverse of B, which we denote by B inverse, B to the power negative 1. This is equal to 1 over the determinant that we obtained in step 1, multiplied by the adjoint matrix, which is the transpose of the cofactor matrix that we obtained in step 3. So this is 1 over negative 10 multiplied by the adjoint matrix, or the transpose of the cofactor matrix. And as we said here, we have matrix multiplication by a scalar value or a constant. How can we do this? We just take this constant and multiply it by each and every element inside the matrix. Thus we will get negative 2 multiplied by negative 1 over 10, negative 4 multiplied by negative 1 over 10, negative 1 multiplied by negative 1 over 10, and 3 multiplied by negative 1 over 10, which is equal to 1 over 5, 2 over 5, 1 over 10, and negative 3 over 10. An important check here, to double check that you did that your answer is correct, you can multiply the B and the B inverse, the matrix B that is originally given to you in the problem, and the B inverse that you obtained here. You should get the identity matrix of order 2, or a 2 by 2 matrix in which all the elements are equal to 0 except the elements on the main diagonal, they have to be equal to 1. Okay, if you didn't get the identity matrix of order 2, this means that something is wrong with your calculations, and that B inverse is not the inverse of B, is not the correct inverse of B, because by definition, if B inverse is the inverse of B and you multiply them, B multiplied by B inverse, you should get the identity matrix of order 2. If this doesn't happen, if you got any other matrix, then something is wrong with your calculations and you need to double check all the calculations. Because the inverse of matrices is very important to help us find the solution for the system of linear equations, which was originally our topic, we will take another example, but for a 3 by 3 matrix and not a 2 by 2 matrix. Okay, because working with 2 by 2 matrices is much easier than 3 by 3 and higher order matrices. Okay, but we'll go through the same steps. The first step is to calculate the determinant. I used the first row here to calculate the determinant, but you can use any row or any column as we said when we considered determinants. Okay, that's why I multiplied 1 here by the cofactor. This part is the cofactor, which is -1 multiplied by I plus j multiplied by the determinant after removing the first row and the first column, which is this determinant 2, 1, 3 and 2. I did the same thing with the 1 here, -1 to the power first row second column, so it's 1 plus 2 multiplied by the determinant after removing the row in which this element is in, which is the first row, and the column in which this element is in, which is the second column. If I removed the first row and the second column, we will be left with -1, -4, 1 and 2, which is the determinant that I wrote here. Then moving here to 1, we will just multiply it by -1 to the power 1 for the first row and 3 for the third column, sorry. And then we will multiply it by the determinant after removing the first row and the third column, which is -1, 2, -4 and 3, which is the determinant written here. If we calculated these determinants, this one, this one and this one, and then we multiplied them to the negative ones here and to the elements here, which is already 1, you will get the determinant equal to 4. Because the determinant again is not equal to 0, we can proceed to step 2 and we can find an inverse. But if this determinant was equal to 0, this means that we cannot find an inverse, and we can just conclude that matrix A is a singular matrix and we cannot find its we cannot find its inverse. If matrix A is a singular matrix, we won't be able to find its inverse. We got the determinant equals to 4, so we proceeded to step 2. In step 2, we need to obtain the cofactor matrix. The cofactor matrix is a matrix of the same order of the original matrix. Our original matrix was a 3 by 3 matrix, so this matrix also has 3 rows and 3 columns. And it's obtained by replacing each element in the matrix by its cofactor. Again, what is the cofactor? We don't write the elements here. We don't write the element that was originally here. We just write its cofactor. What is the cofactor? It's -1 to the power I plus j, or we can simply write the signs that we learned from the sign rule: plus, minus, plus, minus, plus, minus, plus, minus, plus, that we took in the determinants. So it's the sign first multiplied by the determinant after removing the first row and the first column. Here the determinant after removing the first row and the second column. This is the determinant after removing the first row and the third column in which this element is located. And we continue doing the same thing, writing only the cofactors, not the elements, inside this matrix to get the cofactor matrix, which looks like this. After we evaluate each of these 9 determinants, we will get the result. Cofactor matrix as this 3 by 3 matrix: 1, 1, -1, -2, 6, -2, 5, -7 and 3. Okay, now we'll move on to our third step, which is getting the adjoint matrix or the transpose of the cofactor matrix. We simply go here to each row and flip it to be a column. So we have 1, -2, 5. This one will be the second column, 1, 6, -7, and this third row will be the third column now, -2, -1, -2 and 3. Okay, we'll move on to the last step, which is to get the inverse of A, or A inverse. This is done through multiplying this adjoint matrix that we obtained in step 3 by 1 over the value of the determinant that we obtained in step 1. Okay, the determinant was here equal to 4, so we'll just say 1 divided by 4 multiplied by the adjoint matrix here that we obtained in step 3. Again, this is a scalar multiplication or a constant multiplied by matrix. To do this, we will take this constant and multiply it by each and every element in this 3 by 3 matrix as we did here. So this would be the resulting inverse for the matrix, the original matrix A. In order to double check that my calculations are correct, I should multiply the A by the A inverse, the matrix A that was originally given in the problem, and the A inverse that we obtained here, and we are expecting to get the identity matrix of order 3, or in other words a 3 by 3 matrix in which all the elements are equal to 0 except the main diagonal elements are all equal to 1. If you got any other matrix, then there is something wrong with your calculations and you need to double check the calculations. To make sure that you understood what we've said so far, please try to solve this example. This is a matrix C, a 3 by 3 matrix, and we need to get its inverse. I just wrote the final answers here so that if you need to double check your answer, but we will go through the same 4 steps that we just did in the previous 2 examples. The first thing is to get the determinant, and if you got the determinant correct, this would be equal to -1. So this is not equal to 0, which means that we can proceed. We proceed to step 2 and get the cofactor matrix, in which we replace each element here by its cofactor. Then we will get the adjoint matrix, which is the transpose of this matrix. And the last step is to multiply the adjoint matrix by 1 over -1, or 1 over the determinant. And this is done through multiplying each and every element here by 1 over -1. Okay, obtaining this inverse, and to double check that it's correct, we need to multiply this matrix here, the C, by the C inverse to make sure that we get the identity matrix of order 3, or the I3, which is a diagonal matrix. All of its elements are equal to 0 except for the elements on the main diagonal, they are all equal to 1. And please, in case you did this and you have any problems, please take a screenshot of your answer and send me an email so that I can tell you where the problem is. Okay, so far we've considered matrices, we've considered their types, the definition of the matrix, the different types of matrices, and the different operations that we can do on matrices. We will now move on to how to use matrices to find a solution for a system of linear equations. We will use a method that is called the inverse matrix method, and as the name implies, this method depends on the inverse of a matrix. That's why we considered how to get the inverse of a square matrix. The first step is, if you have this system of linear equations, this is what we usually have. We have different unknowns, and these are the coefficients for these unknowns, and these are constants on the right side of the equation. If you have this system of linear equations and you need to solve it using the inverse matrix method, you first need to represent this system in matrix notation, to rewrite all these equations to be in a matrix form. In order to represent the previous system in terms of matrices, we can use the matrix multiplication. We will represent this system as a multiplication of a square matrix A of order n by n, a column vector of order n by 1, which contains the unknowns or the variables, and a constant vector consisting of only the constants of order also n by 1. This is called the coefficient matrix, the A n by n matrix. This is called a column vector of variables, and we call it x, and this is the C. If you did the multiplication of this matrix by this column vector, you will get the system of linear equations on the previous slide. How do we multiply this matrix by this column vector? This is of order n by n, and this is of order n by 1. So the number of columns here is equal to the number of rows here, so we can multiply these two together. How do we do the multiplication? We multiply each row here by each column here. Because this is only one column, so we will only get one value. So if you did this, this would be a11 multiplied by x1 plus a12 multiplied by x2 plus a1n and so on until we reach a1n multiplied by xn. This would be equal to C1, and this was the first equation in the system of linear equations. If you continue the multiplication for all the rows with this column, you will get exactly the same system that is on the previous slide. So yes, we can represent a system of linear equations using matrices by putting all the coefficients in a square matrix, putting all the variables in a column vector, and putting all the constants on the right hand side in another column vector. Okay, we now represented the system of linear equations in matrix form, right, as Ax equal to C. In order to find the solution of the system, this means that we need to find the values for the variables x, y, and z which satisfy all the equations at the same time. It's as if we need to find the value of x, which includes all the variables. X equals what? So it's as if we need to work on this equation to have x on one side and everything else on the other side. Okay, this is how we get the solution for a system of linear equations. The first step is that we need to multiply here by the inverse of A. Why? Because if you multiplied, but of course if you multiplied here by a to the A inverse, we need to do the same thing in the same position. If you multiplied from the left, then you go here and multiply from the left, and as we said, the order of multiplication of matrices is very important. So if I multiplied here from the left by A inverse, I will have A inverse multiplied by A x equals A inverse multiplied by C. So I didn't change anything. I just multiplied from the left, this left hand side and this right hand side by the same thing, so it's as if I didn't change anything, right? But here we have A inverse multiplied by A, and by definition we said that if A inverse is the inverse of A, then A inverse multiplied by A will give me the identity matrix. So now the left hand side becomes I multiplied by x, and the right hand side is still A inverse multiplied by C. But as we said, the identity matrix plays the role of 1 in numbers. So if you multiplied any matrix by the identity matrix, this will give you the matrix itself. So now we managed to put x on one side and everything else on the other side. What is this? This is the solution for the system. If we manage to get the inverse of the coefficient matrix A, and we multiplied it by the column constant vector C, then we got the solution for the system, which is x equals what, y equals what, and z equals what, so that these are the values of all the variables that satisfy all the equations at the same time. Now let's take an example to see how we can do this. And before we take the example, we'll just summarize the steps that we need to do so that we can get the solution of a system of linear equations using matrices. The first step is to represent the system of linear equations in matrix form, in the form of Ax equals to C. What is A? A is the matrix that consists of all the coefficients of the system. What is X? X is a column vector that represents the variables or the unknowns of the system. And what is C? C is a column vector of all the constants on the right hand side of the system. This is the first step. The second one is to find the inverse of the coefficient matrix A. Okay, and then the third step is to find the solution of the system by multiplying the inverse that we got in step 2, the A inverse, by the constant vector C. We'll see the following example. Assume that we have the system of linear equations 3x plus 4y equals 1 and x minus 2y equals 7. This is a 2 by 2 system. We have two equations and we have two unknowns, and we need to solve this system using matrices. As we said, this is done through 3 steps. The first one is to represent the system in matrix form, and by this we mean we need to know what is A and what is X and what is C. Okay, what is A? A is the matrix, the square matrix that consists of all the coefficients. So the first element will be 3. This is the coefficient of X in the first equation. The second element is the coefficient of Y in the first equation. This element in the in the second row in the first column is the coefficient of X here, which is 1, and this is the coefficient, negative 2 is the coefficient of Y in the second equation. So only the coefficients are written in the matrix or the square matrix A. What is X? X is just the variables. All the variables regardless of their names, x1, x2, x and y, y and z, the variables or the unknowns that we have here. And what is C? C is simply the constants on the right hand side of the equation. So this is the first and the easy step, is to just represent this system first in matrix notation. Write the matrix of coefficients, the column vector of the unknowns or the variables, and the column vector for the constants on the right hand side of the equation. The second step is to find the inverse of the coefficient matrix A. Now recall that to find the inverse of a matrix, first we need to satisfy two conditions. The matrix has to be a square matrix, and this one is satisfied in our case. And the second one is that the matrix is non-singular, or in other words, the determinant of the matrix is not equal to 0. So the first step we need to do is to find the determinant of the matrix. And if you find if you consider the previous matrix, the determinant is equal to negative 10, so it's not equal to 0, which means we can proceed to the next step. The next step was to find the cofactor matrix, and we did this before in detail. We need to replace each element in the original matrix here by its cofactor. So we got this cofactor as negative 1 to the power 1 plus 1 multiplied by the determinant after removing the elements of the first row and the first column. And the same for this one, for the negative 1, for the negative 4, and for the 3, as we did in the previous examples. And then the third step is to get the adjoint matrix, which is the transpose of this cofactor matrix. We just flip the rows into columns and the columns into rows. And the fourth step is to find the inverse by just multiplying the adjoint matrix here, this one, negative 2, negative 4, negative 1, and 3, by 1 over the determinant, which is in our case 1 over negative 10. How do we do this multiplication? We take the 1 over negative 10 and multiply it by each and every element in the adjoint matrix. Okay? Then the third step after finding the inverse is just to find the solution. How do we find the solution? We just multiply the A inverse by the column vector C, which represents the constants on the right hand side of the equation. So to find the solution, which is x and y, we will just multiply this. From where did I get this one? This is the A inverse. And from where did I get this one? This is the column vector C, which consists of the constants on the right hand side of the equation. And then what do? We go to the first row multiplied by the first column, and because we only have one column here, so we'll only have one value here, which is 3. We'll multiply 1 over 5 by 1, and then we'll add it to 2 over 5 multiplied by 7, and this will be the 3 here. And because we only have one column here, so we're now done with the first row. We will go to the second row and multiply this row by this column, multiply 1 over 10 by 1, and then add it to negative 3 over 10 multiplied by 7, which is negative 2. Okay? In order to double check that this solution is correct, you go to the original system and make sure that these values satisfy both equations at the same time. Now we'll take another example. We have a 3 by 3 system of linear equations, and we need to solve it using matrices. The first step is to express the system in matrix notation as AX equals C, where A is the square matrix, the 3 by 3 matrix of coefficients, X is the column vector of the variables or the unknowns, and C is the vector of constants. Okay? The second step is to find the inverse of the matrix A. And to find the inverse of matrix A, we need to get first its determinant, right? When we try to get the determinant using the first row here of this matrix, and of course this would be the same if we used any other row or any other column, we found that the determinant is equal to 0. If this is the case, if you try to get the inverse of the square matrix A here, and to do this you did the first step, which is to find the determinant, and the determinant turned out to be equal to 0, this means that this system of linear equations does not have a unique solution. Why? Because we won't be able to get the inverse of A, and we said that to be able to get the solution we need to get the inverse of A and multiply it by C. In case we tried to get the inverse and the determinant turned out to be equal to 0, this means that this system does not have a unique solution. What are the other options for the solutions of system of linear equations? It's either it has no solution at all, or it has an infinite number of solutions. But we won't be able to decide based on what we reached here. We can only say that this system does not have a unique solution, and usually we care mainly about unique solutions. So if the system turned out to have the determinant of the coefficient matrix equal to 0, we just say that we cannot find a unique solution for the system. It either has no solution at all or an infinite number of solutions, and we stop here. Now I'll move on to another example. This is a 3 by 3 system of linear equations. The variables are called x1, x2, and x3 instead of the usual x, y, and z, but this doesn't make any difference. In order to solve this system using matrices, as we said, we have 3 steps. The first of which is to represent the system using matrix notation, which is the equation AX equals C, where A is the matrix of coefficients, X is the column vector of variables or unknowns, and C is the column vector of constants on the right hand side of the equation. The second step is to find the inverse of the matrix of coefficients A, and to find the inverse we said that we need first to get the determinant of A. if you try to expand the determinant of the matrix A using any row or any column, you will find that this determinant is equal to -1. The second step is to get the matrix of cofactors, and again the matrix of cofactors is obtained by replacing each element in the original matrix by its cofactor. So we're not writing the element itself, instead we're writing the cofactor, which is -1 to the power I plus j multiplied by the determinant after removing the ith row and the jth column, and we will do this 9 times for each of the 9 elements in the 3 by 3 matrix. After we obtain the cofactor matrix, we obtain its transpose, which we call the adjoint matrix, or CF, or the cofactor matrix transpose. So we transpose this matrix. Each row is transformed to be a column, and each column is transformed to be a row. The last step to find the inverse is to multiply the adjoint matrix that we obtained here in step 3 by 1 over the determinant of A, which is -1 that we obtained in step 1. And by this we mean that we take the 1 over -1 here and multiply it by each and every element in the adjoint matrix we obtained in step 3 to get the final A inverse matrix. In order to double check, as we said, we can multiply the A inverse by the A, and we make sure that the result is the identity matrix of order 3. This is a 3 by 3 matrix. All its elements are equal to 0, except for the elements on the main diagonal, they are supposed to be equal to 1. Then the third and last step to find the solution for the system of linear equations is to multiply the A inverse matrix that we got in step 2 by the vector of constants C. Okay, and this is a 3 by 3 matrix multiplied by a 3 by 1 vector, and the result will be also a 3 by 1 vector. How do we get its elements? We simply multiply each row by every possible column here. Here we have only one column, so we only multiply this row by this column. We multiply each two corresponding elements, the 1 by the 3 plus the 2 by the 0 plus the -1 by the 2, and we add all these 3 values up to get the 1 here. We do the same thing for the second row because we only have one column, so we now move on to the second row, multiply the second row by each element here in the vector C. So we have 1 multiplied by 3 plus 1 multiplied by 0 plus -1 multiplied by 2. And the last step, because we only again have one column here, we go to the last row and multiply this row by the column vector C, in pretty much the same way we multiply this element by 3, -1 by 3 plus -3 by 0 plus 2 by 2, and here is the result 1. And hence x, which is equal to x1, x2 and x3, is equal to 1, 1 and 1, which means that x1 is equal to 1, x2 is equal to 1, and x3 is equal to 1. And to double check that this solution is correct, you can take these values and go back to the original 3 by 3 system and make sure that these values satisfy all the equations of the system at the same. To make sure that you understand the previous slides, please try to solve these two systems of linear equations. The first one is a 2 by 2 system, and the second one is a 3 by 3 system. In order to make sure that you solve the systems correctly, you just need to satisfy the values of x and y that you get here in the two equations to make sure that the two equations are satisfied at the same time, and also to make sure that the solution you get here is correct. Just satisfy the values of x1, x2 and x3 in the three equations to make sure that they give you the right hand side here. So this is a double check to ensure that the solution that you get is the correct one.